Okay, so that beauty there is 1 kilo of solid silver, which is actually fairly expensive, but it doesn't cost $70 million per kilo. But I'll tell you what does. Okay, so let me start by putting this into perspective. This is a 1 litre pop bottle, and pop is mostly water, and water is about 1 kilo per litre. So this should weigh about a kilo, and it weighs about a kilo. So that's what 1 litre of water looks like. That is 1 kilo of silver. So obviously a kilo of silver is a lot smaller than a kilo of water, and that's because it's a lot denser. In fact, it's about 10 times denser than water. Now let me just put the value of 1 kilo of silver into perspective. A kilo of silver costs about $500. And a new iPhone, this isn't a new iPhone, but imagine it were, for the sake of argument, a new iPhone also costs about the same. But an iPhone or a modern smartphone weighs 200 grams. So in terms of value, they're approximately the same, but of course this weighs about 1/5 to 1/10 of the weight of the silver. So in terms of value per unit mass, a smartphone is about 10 times more valuable than silver. Incidentally, that's what 1 kilo of copper looks like. So if we turn this on, we will get a kilo of copper is a bit on the heavy side, a kilo of silver. So you might be wondering why I've actually got these. And you may recall that there's one of these things that if you lick metal on a really cold day, your tongue will stick to it. And that's because the metal is a better conductor of heat than your tongue is. And these are some of the best thermal conductors that you can get. In fact, I think silver is the most thermally conductive element. So what I was going to do is freeze these and then use the high-speed camera to film my tongue sticking to one of these. But yeah, it's a bit random. And just so you know, so you've got copper there, silver there, and that little guy there is gold. Let me get a close-up on the gold for you. So there you go, that's pure gold. And that's only 1 gram. And 1 gram of gold is about $40, $40, $50, that sort of thing. So 1 kilo of silver is worth about the same as 10 grams of gold, about 10 of these guys. So gold per kilo would be $40,000. Now, gold's actually quite dense stuff. In fact, it's incredibly dense stuff. It's twice as dense as silver here. Now, unfortunately, I don't have a kilo of gold, so I can't show you how small a kilo of gold is, but I do have some tungsten. Now, tungsten has almost exactly the same density as gold. So silver's about 10 grams per cubic centimeter. Gold or tungsten are about 20. So these, if you actually believe it, they weigh about the same. So that's 1 kilo of silver. And this is how big 1 kilo of gold would be. I'm going to stay. So it's absolutely tiny, is 1 kilo of gold. Unfortunately, I've only got 1 gram of it. But if this were gold, that would be worth $40,000. But it wouldn't be worth $70 million. But I'll show you what is. So this is worth $70 million per kilo. Now obviously I don't have a kilo of it. I've only got about 1/3 of a gram. So just for perspective, that's my gold. That's worth about $50. This is 1/3 of a gram of this mysterious white powder, which is worth about $26,000. So what could possibly be worth so much? And it turns out it's potassium 41 chloride. Now with any element, whether it be silver, copper or whatever, there is a nucleus, and that nucleus has a certain charge on it which determines the number of electrons it has, and that number of electrons determines the chemistry. Now, inside the nucleus, you can actually have the same number of positive charges but a different number of neutrons, and so the mass of the nucleus can actually vary even though it's the same chemical element. These are called isotopes. Now, separating isotopes is a mind-blowingly expensive business. So what will have probably happened with this is someone started off with regular potassium, and then they heated it up in a vacuum, and then they fired it down a tube, and they put it in a magnetic field, and the lighter nuclei bend more in the magnetic field than the heavier ones, which don't bend as much. So then you basically scrape off the elements from both of these patches, and one of those would have been potassium-41. And so separating isotopes like this is just mind-blowingly expensive. So the place that many people have come across this isotopic enrichment is, of course, with nuclear bombs and the such like, where you've got to separate the two elements of uranium, 235 and 238. Only 235 is good for reactors and bombs and the such like, 238 not so much. So why would anyone pay $26,000 for some potassium-41? I mean, it's not radioactive, it's just a white powder. So why would someone pay that much money for a white powder? And the answer is for a science experiment. It shows you something that you can't find by any other method. So if you actually want to find it out, you've got to get your 41 potassium. And the reason, the experiment that we're interested in, it actually goes down very much to life and the such like, in that what determines, you know, the shape of my hand and many aspects of it is biochemistry. But if I were to die in the middle of the sentence, all the biochemistry, all the molecules are exactly where they used to be. You wouldn't be able to tell whether the hand was alive or dead. What determines alive or dead for us is essentially the neurochemistry, the electrochemistry of the body, the neurons, and that's determined by the gradients of two ions, the sodium ion and the potassium ion. Now, the most common place you come across the sodium ion is in sodium chloride, which is salt. It's what people put in their French fries. And potassium pick up from a whole variety of other sources. Anyway, so what happens when you have, say, for instance, the sodium ion in water is the water molecules orient themselves around the ion in a sort of very vibrant, a very dynamic hydration shell. It's a three-dimensional structure. And obviously it's a positively charged ion, so the relatively positively charged hydrogens mostly point away from it. And that hydration shell is somewhat different between sodium and potassium. And of course, this is absolutely critical in determining how your nerves function. So if you actually want an atomistic understanding of these problems, you need to know what the hydration of the potassium ion is. And this is a real problem because not only is this a very dynamic hydration shell, it's also tiny. So these are about an angstrom in size, which is about 1/10,000,000,000th of a meter. And this, the hydration shell is only about a nanometer, which is a billionth of a meter. So how on earth could you actually measure something like this? And it turns out one of the ways you can measure the sort of structure of solutions is you fire neutrons through them. But that gives you just a complete mess. It gives you the correlations of everything to everything else, and it's a complete nightmare. But there's this neat trick that you can do if you can get two isotopes of the same element. And that's that you do two identical solutions and you just change one of the nuclei. So potassium for potassium-41. Now the structure of the solution is exactly the same because the structure doesn't depend on the mass, but the scattering properties of the solution are different around this nuclei. So it enables you to just see what's around the nuclei that you've substituted. And that's the experiment that we actually did with this potassium-41. So naturally, whilst I've actually spent quite a lot of money on sciencey stuff over the years, this obviously wasn't one of them. Not even I am crazy enough to spend $26,000 for an experiment like this. It turns out this was actually bought with American money, and it's one of those things that the value of it is basically the energy costs of making it, and there really isn't a market for potassium 41 chloride in the world. So in many ways, once you've done your experiment, you've made your measurements, there's not much else you can actually do with it. So it'd been sat in my cupboard for about a year or something. So the other day when I actually got around to analysing some of this data, there were some peculiarities to it, and it's probably that we don't know the properties of the potassium 41 nucleus as well as we thought we did. So that's why I actually had to go and get this out of my cupboard and dry it down, which is why it's this beautiful fine powder at the moment. And I did this, I kid you not, on my kitchen table, which is now, thanks to, YouTube's been pretty good to me. And so my kitchen is now a really very well set up science lab. So I actually made a specifically designed kit, from the glass blown stuff, specifically for drying this. So yeah, this is now about to go back to the nuclear reactor along with this, which is some very pure regular potassium chloride, which has some really bizarre electrostatic properties, which I could look into sometime. Anyway, so bottom line, hydration of potassium, which when it gets into print will be something people will look to for, they'll reference it for decades, maybe even hundreds of years, as a fundamental piece of knowledge that you need to understand how these ions behave in biological systems, was actually measured with this potassium 41 chloride here, which was purchased with American money, measured in a French nuclear reactor by an Englishman, and this was actually cleaned up on my kitchen table with scientific kit that was actually purchased with YouTube money. Cool, eh?